I want to start today by just introducing myself a bit. My name is Dan Smith. I work on the Java team at Oracle. I've been involved in language and VM feature design over the last 15 years. So I worked on the Lambda project, a lot of different Amber features, and Valhalla. Part of this work is maintaining the language and VM specifications. So we've got a small team of people who address bugs in those documents and update them as new features come along and we need new specification for those. So I work on that. And where I spend most of my time lately is as a coordinator for the Valhalla project, helping keep our design efforts on track and solving all the problems that we need to solve, and then coordinating with the implementation teams to get the features implemented and something we can deliver in a future JDK. Today's talk is indirectly part of that Valhalla work. So the topic for today is initialization. I appreciate you all seeing object initialization on the agenda and being like, that sounds like something I want to hear about. So thank you for extending that trust to me that this is worth your time. It's sort of this is a plumbing thing. We don't really think about, you don't think about, my favorite language initializes things better, and that's why I love it. It's in the background most of the time. But there are problems that can arise in the way Java does initialization. And so we've been looking at those, really putting a magnifying glass on how exactly does initialization work and what can we change about this while still maintaining compatibility. Not dramatically changing the semantics of the language, but doing some small things that can move us towards a better world that address some of those problems. And then having addressed some of the problems I'm going to talk about today, that unlocks some new capabilities. That's where the exciting stuff happens. New features in Valhalla that we're excited to deliver and give great new performance improvements. And some of those things are blocked by how does initialization work. And so we've been working to make sense of it and refresh the foundation on which those new features can build. Let me start zooming way out. What do I mean when I'm talking about initialization? So here's a dictionary definition. To set something such as a computer program counter to a starting position, value, or configuration. So there is an entity, something that needs to be initialized. You initialize things. And that thing has position or value or configuration. We could just call it state. That thing has some sort of state. And we need to set the state to its starting point. Now, if you think about that for a second, you might wonder, what is its state before it's in its starting position? Because it's a thing, it exists, and you need to set it. What was the state beforehand? And if it had state beforehand, wasn't that the starting position? And I guess you can model things that way, but it's actually useful to think about a lot of different program components as starting out created, and then you do something with them to initialize them, and then they're initialized. Some further observations about that. So there's that space between when something's created and when it's initialized. Call that a larval state. And I'll use that word a lot today, larval. It's an entity that exists but isn't fully formed yet. Larval entities don't satisfy the expected invariance. And that's a problem because when you program with things that don't satisfy their invariance, unexpected behavior, dangerous things happen. Programming, in a lot of ways, is about creating this house of cards of different components. Each one has its invariance, and when they all do what they say they do, everything works together. But if one of those cards is taken away, the whole thing kind of falls apart. And so working with larval entities is something that you need to be very careful with. Ultimately, what are these invariants? Developers decide what they are. If I have an object, the object has certain meaning and requirements. Those things are maybe written up in the Java doc, maybe they're just in my head, but they are properties of the program that the developer has created. So ultimately, what it means to be initialized is up to the developer. They decide where that line is drawn, where this thing now has entered the place where it is a fully formed entity. The language and VM, though, also have some invariants, maybe like a least common denominator, things that no matter what programmers have layered on top, we can trust certain things, like type safety. And so there's also a domain agnostic concept of initialization that we can lean into, and that the language can help to provide invariants for programmers that they can rely on as they're layering on their own. Quickly, what are sorts of things that we initialize in Java? Lots of things. Variables, including local variables, fields, arrays, and classes. Local variables, fields, and arrays. In the example on the right there, you can see some examples of all those different kinds of variables and examples of initializing them. We initialize classes. We initialize class instances. And that's sort of an aggregate of multiple variables being initialized. And sometimes objects, even when I've initialized a class instance and the constructor gives it back to me, what I want to do with that object has not been fully initialized yet. So the object, in my use case, is still uninitialized. There's an example here with the hash map where it's a perfectly valid hash map that I get back from the constructor call, but I need to put some things in it for it to be useful. And then at even higher level, components, modules, frameworks, whole systems can be initialized, and that involves initializing lots of subcomponents like classes and instances. Where I want to focus is on variables, and as we'll see, the variables touch class and instance initialization. So initializing a variable, that means setting it to its initial value. This one's pretty straightforward, I think. So a variable exists, initialize it by assigning something to it, now it's initialized. A well-behaved variable is always initialized before it gets used. If you try to read it before it's been initialized, then you're trying to read a larval value. If the variable is final, that initialization is the only initialization. I think that's the intuition behind the word final. It gets initialized, it gets assigned once, and that's the final assignment. So these are properties that we want to, that any good variable is going to satisfy, and that as much as possible, we'd like the language to be able to enforce these things. How do these properties work in practice? Well, method parameters, exception parameters, and pattern variables are nice because they are initialized at birth. They get created and handed off to the program, and the moment that the program can do something with a method parameter, it already has a value. So we can just check those ones off. Those are easy. Local variables are a little more complex. It's possible to declare a local variable and then have some control flow, some logic that initializes it. But as I'm sure you've experienced, if you have control flow that fails to initialize that local variable, the compiler will tell you missed something. And this isn't just it looks like something's wrong here. This is a proof. We've required the compiler to prove that the variable is assigned before you can make use of it. So those ones are in great shape. We can check those off. Fields and array components are where the problems are. So the way these behave is they get a default value. And at creation time, I have a class. When I enter my constructor, all my fields already have a default value set. It is possible, depending on how you try to get to those fields, that you can read those default values. Sometimes that's intentional. Sometimes, let me just jump to this next slide here. Sometimes what you want is just treat the default value like the initialization of this field. Sometimes it's not, and it's an oversight. So in this counter class, I've got a couple of fields, a string and an int. For the int, I may just want to leave it at 0 and not say anything. So in this first constructor, I take in a name, I set the name, I don't touch the count, and that's okay. It's initialized to its default value at 0. That's what I want, and the code can behave as it should. In the second constructor, there's a bug. In this case, I have a different counter I'm trying to copy from, so I copy the count value from that counter. But I've forgotten to copy a name or to provide my own name or do something with the name. And so the name is left at null. That's probably, I mean, potentially you might want the null to be the name of the counter, but in a lot of cases that's not what you want. And you missed the initialization. So then in blue I have the reads. And the risk that we want to avoid here is somebody calls toString and does the read of the name where the assignment to the name has never happened. And there's a way to get there based on using that second constructor. So default values, sometimes perfectly legitimate. Sometimes it's a bug and you need an explicit initialization. Let's think about final fields for a minute. The good thing about final fields is there's some extra language rules that say final fields have to be initialized during construction. So you can't just leave it at its default value. It's also good that we have rules saying there's no mutation of finals allowed in source code after construction or outside of construction. The one thing we don't prevent, though, is sharing the object that is the larval object that's being constructed with somebody else, and that somebody else then going back and accessing the fields. If they do that, they may see default values of the fields that weren't intended to be seen. And if we're talking about a final field now, they're gonna see something at one point in time, and then they'll come back and look at that final field again, and it'll be something different. And you can imagine all sorts of bad things happening in a program that assumes something is final and they see it changing. Because there's this interconnection between different, you can call different methods from constructors and from field initializers, it's really hard to just manage fields. And so to really get to the heart of these problems that I'm talking about and how we can address them, we need to focus on initialization of classes and initialization of class instances. So for the bulk of the talk now, I'm going to look at classes and instances. Classes are a little simpler. Let's start there. What does it mean to initialize a class? Quite literally, what it means is run all the initialization code that appears in the class. And that includes field initializers for static fields. Often that's just like a literal or something, but sometimes it's easy to forget that those field initializers can be arbitrary expressions, and they can execute whatever code they want to execute before finally producing a value, and you complete the assignment. So in that space between when the execution starts and when the field gets assigned, you've got a larval field. Along with static field initializers, there's also initializer blocks. So you can just have an arbitrary block of statements to execute. Usually in this code, what you're trying to do is set up all your static fields. But sometimes there's other things to do too. Sometimes there's some global state somewhere that needs to be manipulated. Maybe you need to register your class with something. As I've said, ultimately what constitutes initializing a class is up to the author of the class. They decide what things need to be set up to call this class initialized. Class initialization at runtime has a state that is tracked by the virtual machine in order to control the status of the class. So it starts out uninitialized when you load a class. At some point, something triggers initialization of the class, and it enters the larval state and begins to run the initializers in the class. During execution in the larval state, there's a lock on the class, so any other thread that tries to access the class has to block until initialization completes. But code in the current thread is able to freely interact with the class and its state. Once all the initialization code completes, one or two things can happen. One is it completes successfully and you enter the initialized state. The other is there's an exception thrown, you go to the erroneous state. In that state, the class is permanently larval. It never reaches the initialized status. It's never been initialized. And in that case, you just can't use it. You're disallowed from ever accessing anything in the class. Okay, as I've said, when you have a larval class, you need to be careful with it because bad things can happen. What sort of bad things can happen? Here's a list of possibilities. You might read a field that is larval. And so you've read it early and you see the default value. There are some obvious cases that language rules try to prevent, but the language cannot lock this down completely. Final fields might be observed to change. I had the example earlier of that. And objects stored in fields elsewhere or somewhere else, or a state somewhere else, all of that may need to be updated in order to achieve a stable configuration, the starting configuration that the author was after. So while those things are not true, the larval class can reveal unexpected state. It can behave in unexpected ways. Unfortunately, it's easy to accidentally trigger initialization or introduce dependencies that you weren't aware of. I have an example here with two classes, app and log. App, if we start with app and we initialize app, it wants to ask the log class for a PID from a utility method, and it's going to set that to a final field. Before it can execute that method call, log has to be initialized. So the mention of log.something triggers initialization of class log and all the code in the log class. So that code is going to execute. You might see the problem now when I get to the initializer of prefix. It's going to go back and ask app for its PID. And so what will it see? A default value is 0. And now all the log messages are going to say that the PID of this app is 0. That's bad by itself. It's also bad because after all this execution completes and we get the real PID back for the app, other code that executes that also depends on this final field is going to get a different number. And you're going to have an inconsistency. Some code thinks the PID is 0, some code thinks it's something else. Interestingly, if you change the order, if you initialize log first, then everything works out. And so this is a very subtle thing that's easy to trip over. What can we do to improve it? In the near term, a straightforward thing we can do is track the state of these static fields at runtime so that whenever I read a field from a larval class, that read consults the state of the field. And if the field hasn't been initialized yet, there's some sort of runtime warning. So a diagnostic that you can request the VM to print or to log with JFR or however you want to view those diagnostics. That will help you see in your program when these things get triggered. You might think that's expensive. It's actually reasonably cheap because this all happens during the initialization, during the larval state. Once you leave the larval state, we can throw all that tracking away and static field accesses are just like they are today. Longer term, we'd like to turn that into an exception. So we'd like to have some mechanism for the compiler or at compile time to say, I want stronger guarantees on my fields, on my static fields specifically. And when somebody tries to read this static field before it's been initialized, throw an exception. And then you do that. When this initialization happens, an exception happens, you see the stack trace and you can figure out what's going on. That's also, again, using the same mechanism, using some tracing of the fields. Pretty reasonable thing to do. The only difficulty is that we're now changing the semantics of the language. I'm not sure how many people depend on this sort of interaction and the ability to read default values, but I'm sure there are some. And I'm sure there's a lot of code out there that just kind of works, even though these things are happening. So I'm not sure we can impose this on everyone and say, as of Java 30-something, you're going to get exceptions when you read static fields. But there's something, we'd like to provide some sort of opt-in to allow people to see those exceptions. Okay, let me switch gears now to initialization of instances. What this means is executing a hierarchy of constructors. So it's a little more complex than with class initialization. There's code in each class. Constructors, there's also field initializers for the instance fields. That code needs to be run. There's also instance initializer blocks. They don't get used very often, but that's some extra code that needs to run. Again, like with classes, the goal of instance initialization is usually to set up your instance fields. But there's other things you might want to do. You might have some global state or a static field to manipulate or something like that. Programmer decides what an initialized instance means. What anybody looking at the class can say is that the class is initialized when the constructor returns. So this illustrates the timing in a little more detail. The purple bit, we say runs in the early construction phase, and the pink bit runs in a late construction phase. So the purple part there is an argument to a superconstructor. If I call that constructor, the first thing that's going to happen is I'm going to compute the super argument, or the super, not the super, in this case I'm calling this, compute the constructor parameter. And that involves executing this expression, running whatever code is in that expression. That runs early. There's also some when you capture things, setting up the fields of your captures, that's something that runs early in the purple phase as well. After we get back from a constructor call, then we run all the late stuff. There's some implicit code that happens during construction. So a lot of times you don't think about this kind of fine-grained detail. It just happens. But in my second constructor, the first thing that happens is an implicit super call, hands off to the super constructor to do whatever it needs to do, then it comes back. Second thing that happens is we run initializers. So that would be the list initialization. And then after that, whatever else is in the constructor runs. Now there's a JEP in 24. It's been a preview feature for a few releases called Flexible Constructor Bodies. And what this JEP does is it enables additional code to be written to execute in the early phase. So let me illustrate. Now my first constructor there has some computations. Rather than happening between the parentheses of the this call, I can have some statements that do the computation. And when I've worked out my parameter, I can then hand it off to the this call to the other constructor. So now there's more things that are happening in the early phase. It's also possible to assign fields now in the early phase using this preview feature. So you can, if you have a bunch of fields with simple initializers, you can just go ahead and initialize them in the early phase. There's a state for instance initialization, just as there's for class initialization. It's pretty similar, but it's a little more complex because we have this early and late split. You start out with an uninitialized object, invoke a constructor. Execution starts, as I said, with the early code, and that's in the purple bit. And then you hand off to a superclass, and this recurs. So what you see on this next slide is I've got a class C. It's going to hand off to class B, then to A. Each one of those execute their early code. And when you finally reach object at the top, now you shift into the late construction phase. And we work our way back down, A, B, and C in the opposite order. I think when we're writing constructors with hierarchies, people are used to the superclass is going to go first, and then I'll go next. But with this additional space for code in the early phase, it goes all the way up and then back down. And so the timing can be a little trickier. After all of that execution completes, again, you can either complete successfully, transition to the initialized state, and congratulations, you have an initialized instance, or something went wrong somewhere in that hierarchy, anywhere in the execution, an exception gets thrown. And at that point, you have an object that can never be used. And the virtual machine will actually prevent you from ever attempting to do anything with that object. We have larval objects, just as we had larval classes that require the same amount of care. I spent a lot of time talking about the early and late phases because there's an important distinction. In the early larval phase, the instances are limited. There's not much that you're allowed to do with this. You can assign to its fields. You can't hand that object off to somebody else. You can't execute a method somewhere. You can't invoke your own instance methods. And because it's constrained so much, nobody else can get a hand on this larval object and do something unexpected with it. In the late phase, then it becomes unrestricted, and you can share this with other code. You can read fields and get default values. Final fields can be observed to change. There may be additional updates to other code somewhere, other state somewhere that needs to happen. So the insight looking at this division is, wouldn't it be great if anything that can run in the early phase actually does run in the early phase? Run it in the early phase, then you know all that initialization is going to happen before anybody can touch your object. Even if you don't know what your superclass is going to do. Before you hand off to your superclass, set up all your state, and you know that for your purpose, in my class is properly initialized. In the near term, how can we do that? Well, we can't go in and start changing the order of things, the order of code execution. Lots of bad things could happen if we just imposed that. What we can do is provide some compiler warnings that encourage a convention that if code needs to run in the late phase, the timing should be explicit. And what I mean by that is if you need to run something in the late phase, include an explicit supercall, and then provide the code that needs to run late after that. So what that means is instance field initializers, they're not explicitly after a super. Treat them as if they were going to run early, even though they don't, they run late. And that means the compiler can go in and look at those initializers and see if there's any mentions of this, any instance method invocations. And if there are, provide a warning. Same thing with constructors that have implicit supercalls. The implicit supercall still goes at the start, but in the body, treat that code as if it were going to go in the early phase and look for any uses of this that could expose the larval object to other code. So, okay, we turn on those warnings. People can opt into them, and they get some extra warnings. Oh, one more thing here. Field reads are one thing you might want to do with this that is actually pretty innocent. If the field has been assigned, and we're talking about local code, we can see that the field has been assigned. There's nothing particularly wrong with going in and reading the value that you just assigned to it. And so that's something we can support. And we could add that behavior to the early phase. And then somebody can opt into these warnings, and they get warnings of anything else they try to do with this. And when they see those warnings, what they can do is put in an explicit supercall if necessary, so that all the early code that can run early is placed in the early phase. And then things that have to run late because of the dependency on this, they appear after the supercall. Longer term, what we'd like to do is change the timing with, again, some sort of compile time mechanism, so that for certain classes or for certain configurations or something TBD, all of the code in those places I just mentioned, in field initializers, in implicit supercalling constructors, that all runs early. And as you can see in the gray there, the implicit stuff, initializers still run at the very start. Then you run the code, and then the implicit super can go at the end. So if you turn on the warnings in the short term, those warnings will prepare you for being able to opt into this in the longer term. And you address any errors when you get compiler errors by, again, using an explicit supercall to differentiate between what needs to run early and what needs to run late. Is this a realistic thing to ask people to do? We did a survey of some open source code looking for uses of this during instance initialization. And a couple of data points out of a lot of the data we got. 2.3 million normal stateful classes that declare some fields. 1.1 million fields in those classes have field initializers. Only 3% have a this dependency. So it's almost always the case when you initialize a field that could run early. There's not much reason not to run it early. And about 1 million constructors that have an implicit supercall. 13% of those have this dependencies. So if you were to turn on the warnings, you'd get a few warnings in your code. This isn't, there's going to be some number of indications of something to clean up. But this feels like doable, something that you could opt into and look over your code and find those places and address it. I want to make a quick mention of arrays, finally. Those are the other kinds of variables that are difficult to handle. The right way to think about arrays is they are always initialized with something when you create an array. The problem is just sometimes you initialize it with default values, and you don't want default values. So as a way to help address that, in the future we'd like to support things like give me a new string of length 3 and fill in all the strings with the empty string, if that's the starting place I want to have. Or let me compute for each entity, for each component. Let me give you a lambda that computes the things to fill in. So, got a fan, I like it. So when you write your code in that way, there is no risk that those default values, if for your purposes those are invalid data, by being able to fill in your array as it's created, there's no risk that somebody's going to see the array before it's been filled in. Okay, for the last bit, let me step back and say this sounds like a lot of work, a lot of tweaking, subtle, long-standing behaviors. Why should we bother with this? There's a few bugs that we can catch, but it seems like it's got to be more important than that to justify the amount of work that it is to implement these changes and for the community to adopt a different style of writing constructors, for example. So why is this important? For one thing, initialization bugs are subtle and hard to see. I had an example of classes where they were interacting in a surprising way. Here's an example of records where somebody does some validation in a compact record constructor. And if you've used these in records, you know there's some implicit code inside that record constructor. You might not know off the top of your head where that code goes, so I've helpfully illustrated here. The constructor starts with a supercall, which doesn't do anything. Record is an empty class. Then the validation code is happening, and then finally the assignment to field happens. So if I am, in this case, I'm invoking an instance method that I inherited from a superclass. Superclass exists to do some data validation, and it talks about this. It wants to print this, and when it does that, it's going to print this record before the field has been initialized. So that's one problem. These sorts of bugs, they happen at class creation, they happen with instance creation. The second problem, value classes in Valhalla have to initialize their fields before they share the larval object. Because the way value classes work is they don't have identity, they don't have a location in memory. They can be freely copied around, duplicated. Different people can encode the same object in their own ways. That kind of stuff can't happen if I'm still in the middle of initializing the fields, because I'm going to try to write to memory in one location and somebody else's location won't get updated. So in the comment there at the bottom is an example of what a layout for a object that contains value object fields might look like. It can compress all the data right there, directly embedded within the object. And can't do that if the object might be larval and there might be coming changes. So with a value class, all the fields are final, and they all must be initialized early. When I talked about changing the timing of where initialization happens during instance initialization for a value class, that's the way it is out of the box. When you declare a class a value class, the initializers and the implicit super calling constructors all run in the early phase. Yeah, so that's another thing. In order to make value classes work at all, these are features that we need. A third example, we want null checking of variables, preventing a variable from ever being null. So if a variable can't be null, but it stores a reference, what is its default value? The answer in a lot of cases is there is no default value. So what before was an annoyance, you could read a field and see a default value that wasn't the intended initial value. Now it becomes a crashing VM or something because you're seeing data that was never initialized and is not meant to be read. So to properly support a null restricted type or a null checked type, the initialization of those fields has to happen in the early phase. And for classes, for static fields, those fields have to be checked. We have to get an exception when you try to read a null checked type before it has been assigned. For arrays, we can't use the default value array creation. We need to use one of those other array creation methods that provides an initial value to populate the array with. And fourth thing, when we combine these two features, value classes that can be freely copied around and re-encoded with null-checked variables that can't store null, that enables the VM to compress the storage into kind of its minimal footprint. So I have a point class here. It contains two floats, two 32-bit values, and I have an array of points, 1 million points. Ideally, we'd like that layout to consist of just pairs of 32-bit values in each entry in the array. No pointers to something else, no extra true-false like I had in the previous to keep track of nulls, just the float data. And in order to achieve that, again, those variables, in this case, this array, has to be initialized with something out of the box. We have to prevent anyone from ever being able to interact with the larval array data. So that's all I have here. I'm happy to take some questions from you, and thank you for being here. Go ahead.
Hello. So what if the initialization has side effects? Then if you move it around, you will basically change the side effects. So how do you handle that? Yes.
So the question is, what about side effects with timing that are not explicit, but it's expected that one piece of code will execute before another piece of code. Within a class, if you notice when we were changing the timing, the order is still the same. You have initializers that run first, then you have the constructor. If you're physically moving the code within your class, then that's something you should think about. There's a possibility of interactions between a subclass and a superclass. Maybe the subclass does something, and it expects the superclass to have already done something first. So that's a reason why there needs to be an opt-in, so that somebody can say, okay, this is a class that I'm willing to change the timing of, and if there are those sorts of timing issues, I'm willing to take on that risk and address it. Yeah.
You talked about in the early phase you can't call methods, which makes sense. Is that instance methods or static methods or both, and why?
In the early phase? Right, so the early phase prevents any execution of instance methods. Instance methods, anything else you might want to do with this, like create inner classes. There's a list of about 5 or 6 different syntactic forms that are not allowed in that place. And that's actually not new. That's been the rule. It used to be treated as if it were a static context, basically. You can kind of think of it that way, a static context that lets you address the fields to assign them.
Just a quick question. The larval state that you were describing, is that in the JVM now, or is that, do you actually track a larval state as such in the JVM, or is that something that's coming in the upcoming JEP?
So there is this larval state for classes. That one is explicitly in the JVM. It doesn't use the term. It just says the class is being initialized or something like that. But that is, yeah, part of the specified mechanism for initializing a class is to keep track of this state. For instances, it's not exactly described as a state, but we keep track of, in the code of a constructor, whether you are operating on something that was just before and after the supercall. So there's a transition that happens between the code before the supercall and after the supercall. And if you try to violate the rules, you'll get a verification error in the bytecode.
Oh, okay, and is that in the class file structure itself, or is that something that the JVM figures out on the fly?
It is part of the type system of the verifier. And so there's the stack map table attribute where you can talk about the type of the thing you are initializing, and the type changes from an uninitialized thing to a regular class type.
Ah, terrific. Thank you.
Yes. Okay, I wasn't sure how I'd be on timing, but we got there, so good. Thank you all. Appreciate you being here.